In part 4 of module 1, we're going to cover set operations and compound inequalities. Friendly reminder, you need to be completing your guided notes while you watch this video. So, what is a set? Well, a set is a collection of objects whose contents can be clearly determined. So, we call these objects elements of a set. So, for example, we write the set of counting numbers as 1, 2, 3, 4, 5, 6, and we use braces or curly brackets to represent our set. So some examples are, we have the set of natural numbers n can be denoted n equals 1, 2, 3, and so on. An example I like to think about in order to think of what's clearly defined is I like to think of the set of objects that are red, right? So what are some things in the set of objects that are red? Well, we could have apples. We could have a fire truck, right? We could have a strawberry. We could have a stop sign, right? But an orange wouldn't be in there, or a traffic cone, or grass, right? This is a set of only things that are red, right? Since it's clearly defined. We could also have a set of fruit, right? And we can know that there's going to be some overlap between the set of fruits and the set of things that are red. So for example, for fruit, I could have apples. Those are red, but not all fruit's red. I could have a banana. I could have an orange. I could have some grapes. Those could be green or purple, but sometimes they're called red. Well, the idea is that these sets are clearly defined, right? And we can tell what's in them and what's in is not. In a fruit, mac and cheese is not going to be in fruits. Fire truck's not going to be in the set of fruit, right? They're clearly defined. So if we're looking for the intersection, we're looking for, if I have two sets, A and B, the intersection is the set of all elements in both A and B. So in both of them together. So we can think of this as if I had my set of things that were red and fruit, this is going to be where red and fruit are both true. So this would be apples. This would be strawberries. This wouldn't be a fire truck. Even though it is red, it's not a fruit. This wouldn't be an orange. Even though it's a fruit, it's not red. So it's objects that meet both criteria. So let's let U be our universal set. That's the set with all the numbers we have to play with. In this case, it's a bunch of odd numbers. And A, B, C, and D be defined as follows. So I'm going to find the intersections. I want to find the objects they have in common. So if I'm looking at A intersect C, I want to see, okay, what do A and C have in common? Well, they both have a 3, and they both have a 9, and that's all they have in common. So the intersection of A and C would be 3, 9. It'd be a smaller set that just contains 3 and 9. I could also look at the intersection of B and D. So I'm looking for what B and D have in common. B is 3, 7, 9. D is 1, 13. They have nothing in common. So I could make a little brackets with nothing in them, or I could use this symbol for the null set. That's the symbol for the empty set, meaning there's nothing in there. Next, I could have B intersect our universal set. So what does U and B have in common? Well, they both have 3s, they both have 7s, and they both have 9s. So it would be the set 3, 7, 9, which is the same set as B. So I could also just write B if I wanted to. So that's for intersection. I want elements in both A and B. I wanted things that were both red and fruit. We also have to look at the union of sets. So when I have two sets, A and B, the union of A and B, written A, this fancy U, B, is the collection of all elements in A and all elements of B. But we only write each element once. So if I wanted everything that was in red union, fruit. We would have the things from the intersection in here. We would have apples because they're red and fruit. We would have strawberries. But we would also have a fire truck. We would also have grapes because grapes are a fruit, but they aren't red, and I need all fruits. And fire truck is red, but not a fruit, and I need all things that are red, right? This is a clearly defined set, so we're collecting everything. So if we had the same sets as in our first example, here I want to find A union D. So I'm going to take all the elements in A. I didn't mean to write that. So I'm going to have 1, 3, 5, 9, 11. I missed 7. 7. Throw it in there. And then in D, I have 1 and 9. Well, those are already written down, so I don't need to write them down again. And 13, right? And when I take A union D, I get the entire universal set. So I could write a U for our universal set, or I could just list all the elements. Here I have B and C. If I want B union C, I need all elements in B, and then all elements in C. So C already has a 3, it has a 9, but it also has an 11. And a curly bracket to denote it's a set. So the reason I'm talking about intersections and unions is we're going to start looking at compound inequalities, which is when I have inequalities that I'm looking for the union of or the intersection of. And means intersection. I kind of remember it because the N looks like the intersection, and or means union. So if I'm looking for the intersection of these two inequalities, I'm looking for where their graphs overlap. So here, I'm going to go ahead and solve the equation on the left-hand side. I have x plus 1 is less than or equal to 9. I subtract 1 from both sides. I have x is less than or equal to 8. And then in another color, I'm going to add 2 to both sides on this equation on the right. So I have x is greater than or equal to 5. And I need both of these things to be true. So let's go ahead and label our number line. So I've got 4, 5, 6, 7, 8, 9. So I know that I need x to be less than or equal to 8. So 8 is included because it's less than or equal to. And since it's less than, I shade to the left. And I know I need x to be greater than or equal to 5. 5 is included. I shade to the right. So I need everything that is both blue and orange. I need 5 all the way to 8. I need everything that was with blue and orange. So my solution would be everything from 5 to 8, where 5 and 8 are included because those endpoints are included. We're looking for the intersection. We're looking for the overlap. When I see the word and, it means intersection, it means overlap. Let's look at another intersection example. Here I have x plus 2 is less than 5. So I'm going to subtract 2 from both sides. I have x is less than 3. I'm going to add 10 to both sides. I have x is greater than 12. And I can go ahead and label my number line. Maybe I'll do it counting by 3. Save us some time. So in blue, I'm going to graph this x is less than 3. Here's my 3. It's not included, but we needed to circle it because everything really close to 3 will be. And I shade to the left. We're looking for their intersection. In orange, I'm going to have x is greater than 12. 12 isn't included. I shade to the right. I'm looking for the intersection. Is there an intersection here? No. My blue and my orange graphs do not overlap, so there is no solutions. This is the empty set or the null set, right? We can do the empty set, brackets with nothing in it, no solutions, works as well. Well, there's no solution set if we're going to be precise. Next, I have negative 3x is greater than 7, and 5x is less than or equal to negative 20. I'm going to go ahead and divide both sides by negative 3. I have x is less than, you got to flip the sign, negative 7/3, that's negative 2 1/3 to make for easier graphing. I divide both sides by 5. I have x is less than or equal to negative 4. So let's go ahead and label our number line. I think you guys on the guided notes already have a labeled one. That's so nice. Okay, I know x is less than negative 2 1/3. So here's negative 2 1/3 right about here. I've got an open circle, and it's less than, so I shade to the left. And I didn't mean to do that in orange, but we're going to run with it. And then in blue, I have x is less than or equal to negative 4. Well, negative 4 is included, and since it's less than, I also shade to the left. So here, the question is, where is blue and where is orange? So I can write my solution set in green. Well, over here is negative infinity. And so we can see my blue and orange overlap from negative infinity. And then we take a look, and they overlap all the way to 4. So my solution set would be from negative infinity to 4, where 4 is included because that endpoint is included. So those were some intersection examples. Let's look at some union examples. So or means union. When I see an or, I like to write this U to remind me I'm looking for the union. In this case, I want everything that'll be graphed in orange and everything that'll be graphed in blue. I don't care what color it is as long as it's on my graph, and we'll write our solution set in green. So over here, I have negative 4 is less than 4x. I divide both sides by 4, which you couldn't see very well. I'll fix it. So divide both sides by a positive 4. I have negative 1 is less than x. Then I also have negative 3x is less than 9. I divide both sides by negative 3. I get x is greater than negative 3. So we're going to graph both of these. Let's go ahead and label our number line. 0, 1, negative 1. Okay, so here I have x is greater than negative 1. So negative 1 is less than x. Negative 1 is not included. X has to be greater than it, so I shade to the right. Here I have x is greater than negative 3. So I have negative 3, but it's not included. Greater, so I shade to the right. Now, I want my solution to be everything that is orange and, not and, but together with everything that's blue. So my solution is going to be everything from negative 3, where it gets a parentheses because it's not included, all the way to positive infinity. I'm not looking for the intersection. I'm looking for the union. I need everything orange, everything blue, and everything that's both blue and orange. Let's do 2 more examples because this is fun. Okay, so I have negative 4x is greater than or equal to 8. I divide both sides by negative 4. I flip my sign. I have x is less than or equal to negative 2. I also have 5x is greater than negative 15. I divide both sides by 5. I get x is greater than negative 3. We can go ahead and label our number line. Negative 4, negative 3, negative 2, 0. Okay, x is less than or equal to negative 2. Negative 2 is included. Less than means I shade to the left. Greater than. X is greater than negative 3. Negative 3 is not included, but I shade to the right. My solution set is going to be everything that's orange, everything that's blue, and everything that's both orange and blue. Well, that is going to be everything. That's going to be all real numbers. I've covered everything on the number line. So I can write that as negative infinity to positive infinity. Last example, I know we're so sad. I have negative 2x is less than 6, or 4x is less than or equal to negative 20. So we solve for our x's. I get x is greater than negative 3. We had to flip the sign, right? Don't forget to flip. Divide both sides by 4. X is less than or equal to negative 5. So I have x is greater than negative 3, and x is less than or equal to negative 5. So let's go ahead. I'm going to graph x is greater than negative 3 in blue. So I circle negative 3 and I shade to the right. And then in orange, we have x is less than or equal to negative 5. So I have negative 5 and everything less than negative 5. So my solution set needs to be everything that's orange, everything that's blue, and everything that's both orange and blue. Well, there's nothing that's both orange and blue here, and there's a gap in my solution set, it seems, because I know I have from negative infinity to 5, but and that 5 should have been included, so we give it a bracket. Since it was less than or equal to, that 5 should have gotten a closed bracket, and should have gotten a bracket and a closed dot. And then I also have from negative 3 all the way to positive infinity. That's over here. So my solution set is from negative infinity to 5 together with, or unioned with, negative 3 to positive infinity. So it's okay for our sets to be disjoint, not overlap. We just need to remember to use a union symbol when we write them to show that they're together.